Welcome to qnawire.
Now we have a mass, kind of this is the obligatory problem of a block sliding on a surface with no friction in this case, and it's connected to a rope which goes through a hole in the middle, and then we can pull it so we can change the length of this rope here, so we can change the radius of rotation. The block weighs 0.13 kilograms. The initial radius that it's rotating about this center is 0.8 meters, and it has initial tangential velocity, so v theta naught is 4 meters per second. And we're told that the tension in this cord can go up to 30 newtons before it breaks. So they ask us how far can we pull this down or pull this block in before the rope breaks. So we know from a free body diagram here that T must equal the mass times the acceleration, which is the centrifugal acceleration, and that's r omega squared, or v theta squared over r, tangential velocity squared over r. So well, we need what the v theta is at when the rope breaks. So well, there's no net. The force on this rope here is along the axis here, and so we don't have any torque, net torque on this block here, because the only force acting is through the axis of rotation. So we have angular momentum is conserved. So the initial angular momentum is m r naught v theta naught, and the final angular momentum is m r1 v theta 1. So that tells us that v theta 1 equals r naught over r1 times v theta naught. Now that's what we want. So T1, which is going to be set to T max, is v theta 1 squared over r1. So we can plug in, we have m 1 over r1, and then v theta 1 is r naught over r1 squared times v theta naught squared. So we plug this into here and then set r equal to r1. And then we set that all equal to the maximum tension, so that this would be the length when the rope breaks. So what we can see here is we get kind of an interesting thing. We have 1 over r to the 1 over r1 cubed here. So we solve for that. We get r1 cubed is m r naught squared v theta naught squared all over T max. So r1 is the cube root of that. And we have values for all of these things, and plugging them in we get 0.354 meters. Now we can also check and see, does this make sense? Well, as T max grows, this shrinks, which makes sense, because as this gets stronger, then we can pull it in farther. As all of these things grow, R1 grows. So basically, if we have more mass, we're not going to be able to pull it in as far, which makes sense. Basically this is the initial angular velocity here, right? Squared. So if that goes up, no, that's not the initial angular velocity. That is the initial. That's kind of like what is that? Not sure what that is, but let's say r naught goes up. If v theta naught stays the same and r naught goes up, that means we have the angular velocity is r v over r. So if r goes up, this goes down. So it makes sense that we have then that this goes up. And then as the initial as this initial angular velocity increases, r1 also increases. And again, that's a little counterintuitive a bit, but you can basically kind of trace it back to the fact that our tension, our the tension in the cable goes up like that. But then we have the goes up, with v theta squared. So then when we get back into here, as this went up, then the tension goes up as this thing goes up. So that means that R1 occurs in the denominator here. So as R1 increases, so say R1 increased, then T max is going to go down. Right? If we were just looking for what the tension is as a function of R1, as R1 goes up, T1 goes down. As R1 goes down, T1 goes up. So again, you can kind of trace it back to this. It's a little counterintuitive here, but again, it's good to kind of try to argue that the form of this expression makes some sense. It's a little hard to argue here, but if you go back here, it makes a lot more sense that T goes up as R1 goes down, and T goes up as V naught, or as V theta naught goes up.